And now the first lesson in chapter 2 is this problem of two-dimensional steady state external flow. The project of figuring out the distribution of flow, obviously pressure field as well, that problem is governed by the first three equations. And if you specify the solid object that comes in contact with the flow, because you have to have a solid object, meaning a drawing, inside the flow field. You must have one because you must have a temperature difference. The solid has one temperature, the fluid far away from the solid, another temperature in external flow, far away from the solid, and therefore you'll have heat transfer. That problem was impossible to solve for about 100 years, meaning the 1800s. The equations were figured out by Navier. By the way, these equations are partial differential equations, versions of F equals ma invoked at the small small volume element. And so to translate Newtonian mechanics into the language of infinitesimal calculus was the step made by Navier. In my opinion, these are the equations of Navier, actually, according to history. Today, they are known as the Navier-Stokes equations. It's worth asking why they're called Navier-Stokes equations. Navier published these equations in the French Academy of Sciences. He was a contemporary of Fourier, but there are several others who improved on him. Saint-Venant, and Poisson, and Fourier, in this sequence, all within less than 10 years. Fourier is known for heat conduction, but if you read the Fourier's book begins with these equations, the equations which are more general for convection. In the very beginning, Fourier acknowledges the development which was due to Navier, and then he focuses on the absence of flow and does solid body conduction. That's Fourier. But when Navier published these equations, Stokes was 2 years old. And then obviously one generation later, Stokes, people say, improved the Navier's equations and published them in English. You learn here how important publishing in English was, meaning how important it was long ago, not today, long ago. So that's the origin for the Navier-Stokes terminology. Anyway, impossible to solve. In 1904, Ludwig Prandtl a young mechanical engineering graduate from the Technical University of Munich, had an idea. And the idea is a pictorial one. His interest, in fact, he was commissioned by the Kaiser to lead a brand new institute to develop the airplane as a useful object, useful in the military as well. And the airplane suffered from the need to have power, power to overcome drag. And the drag was due to skin friction, meaning here's the airplane going faster and faster. And the faster, the bigger the friction force against the ambient. And so how to predict the friction force? Not only the size of it, but how that force depends on the surface of, in this case, the wing and the shape of the wing. And that was the problem. And so here comes Prundle and says, hey, folks, if this is the wing, of course, try the simplest first as a flat surface. And this is the flow field in y versus x. If you're interested in friction, you're not interested in you should not be concerned with the entire world, the atmosphere that flows relative to your wing. Of interest is a smaller control volume of flow that touches the surface. And this is two-dimensional. It has a length L and thickness delta. L is up to you because you know the swept dimension of the wing, so you know this. But this other thing, the thickness of the flow volume in which fluid friction manifests itself is unknown. Or not the unknown, but it is the unknown. Why is that the precious baby? Because here's the fluid coming in with a free stream velocity that we will call U infinity. Of course, this fluid, because of friction, just like honey on your teaspoon, sticks to the surface. And it sticks here, and it sticks more here and more here, so that downstream, the velocity profile still has U infinity far from the plate, but zero at the plate. In other words, there's a gradient of velocity U in the vertical direction, which, if evaluated at the wall and multiplied by Newton's viscosity, is the shear stress, the friction force per unit area experienced by the wall. And this tau of units Newton per meter squared is, in fact, the object of the game. Wanted was the ability to predict skin friction once and for all. So this was the breakthrough, meaning that, as you'll see next, if you make the additional assumption, which is implicit in the drawing, the assumption that the layer is slender, so assume then you have the ability to simplify these equations and then render them solvable. What do we mean by that? Well, you'll see very soon. In fact, I'm going to erase everything except these three equations. Don't forget this Navier-Stokes. I published a paper about not just Navier and the fact that he is still being mistreated by history, but others of his type who paid for their misfortune of not publishing in English. Yes, I did. I called it nationalism and forgetfulness in in the history of science, and called this little drawing boundary layer. In fact, in German, Grenze means frontier. That is what you run to if you want to run away from dictatorship. You follow a beeline to the Grenze, to escape to Switzerland, if you think about the 1930s. So, boundary layer theory. Theory means the act of predicting. You don't need to measure something if you know the theory that works. And the theory is simply this assumption. That is, if you're wise. If you don't like writing, you call it BLT, for boundary layer theory. So next time you go into one of these sandwich shops and you ask for a BLT, think of me, okay? What does it mean? Well, it means this, because now we know scale analysis. What happens to these equations if some of these terms are negligible because of this slenderness assumption? Let's find out. So the implications of this, these are the implications. So mass conservation, what is the order of magnitude of du dx? You don't engage in hand waving. You just look at the drawing. The change in u corresponding to the change in x. X changes from 0 to L. So instead of this, I put L in the denominator. U changes from solid fast to not so fast. In some places, 0 at the wall. So the change in the little u is u infinity. So the order of magnitude of the first term is u infinity over L. There must be an order of magnitude for the second term, obviously, because the change in the vertical direction is of size delta. What is the necessary change in the transversal direction, called little v? You may think that this, because it's laminar flow, this flow is rectilinear. It is almost, but not exactly rectilinear because of friction. The flow comes in and it starts piling up on the wall. Therefore, the slowed fluid is carrying on its back the faster fluid and deflecting it upward slightly. So the streamlines are this way. In other words, there is a small vertical component to this flow, one that I'll call V infinity. The velocity component piercing this upper surface. Also unknown. Unknown, delta is unknown. But what we know for sure, when we have an equation with only two terms, we know exactly that one will be exactly the same size as the other, because they must add up to 0. And this is why mass conservation is the way to begin, to say that for sure one is of the same order as the other. And at this stage, we've achieved, we taste the promise of scale analysis, which is to forget about PDE and begin to work with algebra. So this has been checked. What about the momentum equation in the x direction? We reason the same way on this line. The order of magnitude is, again, I will not belabor the point. Now we know what to do. Okay, this is u infinity, this is L. The second term is v infinity, and then u infinity over delta, and then comma, where the equal sign was. And then I'll just write 1 over rho, and if there's a pressure variation in this flow, I call it delta P, and then L. And then 2 more terms. In fact, I'll write them nu, and then in the brackets, u infinity over L squared, comma, u infinity over delta squared. Three things happen almost automatically at this stage. The first is due to the slenderness assumption. If you have this in your head, then clearly 1 over something very, very small is much bigger than 1 over something very big. And that means that you can neglect this scale. That's the equivalent of neglecting this term. That's the first thing. The second thing is answering the question of which of these first 2 terms can you neglect? This is a trick question, but the reason why I started with mass conservation is for you to recognize balloons. This balloon is the same balloon, is an order of magnitude quantity, and you see it here. Which means that you cannot neglect one relative to the other. You have 2, like A plus B, added. Here's what you have. On the left-hand side of the momentum equation, you have A plus B, except that A is of the same order as B. And one of the rules of scale analysis, if you read the end of chapter 1 in the textbook, is that the sum of 2 terms, where the one term is of the same order as the other, is of the same order as either of the 2 terms. In other words, A plus B is of the order of A or of the order of B. So that's maybe a little counterintuitive, but it's the kind of simplification that you can take to the bank. You deposit $1, and you said, actually, this $1 of mine actually is $2 because I'm dealing with you in scale analysis. Or if they tell you that you owe $2, you give them 1, the same order of magnitude. Okay, so the left-hand side, this thing, which I will put in a box, this is the left-hand side, is simply u infinity squared over L. So that was the second move. The third move, and this is a move that I skip, it is detailed in the book. If I play this order of magnitude rewriting of the momentum equation in the y direction, I discover that the pressure field, so that is if m in the y direction is expressed by scale analysis, I discovered that the pressure field in a slender layer of fluid is at best a function of longitudinal position. In other words, the pressure field in general is a function like everything else that I erased, x and y. But because of slenderness, and by that I mean delta much smaller than L, it is at best a function of x. That is a property or a feature of the boundary layer because the boundary layer is slender. It means that partial of P with respect to x is in fact straight of P dx, meaning the pressure does not depend on y, and that means that the pressure inside the slender layer is the same as just outside. And what is the pressure outside when the flow is uniform? Think of the airplane wing being dragged through the atmosphere of uniform pressure. This P infinity is a constant, so this entire string is not only negligible, it is zero. And that means you forget about that. And the right-hand side reduces to eta times this term. So the momentum equation is this left-hand side plus this particular right-hand side, which is nu, and then u infinity over delta squared. Simple as that. Remember, you have unknowns here. One was V infinity, the other one was delta. But this is the moment where you begin to experience Prandtl's euphoria. He did not solve his problem with scale analysis. He solved it, you'll see a little bit later, meaning during the next lecture, not next, 2 lectures downstream, as exactly or as laboriously as imaginable, because he wanted to be perfect. This was an unknown. It is not an unknown anymore. If you turn the crank, you get the delta squared the same as L over U. By the way, there was this nu here. So, and then to make this result dimensionless, you divide by L squared to figure out the slenderness of this boundary layer. And then you take the square root of everything. And you arrive at delta over L being the same as the Reynolds number based on L to minus 1/2. Where the Reynolds number, this is our first encounter with this dimensionless group, emerges naturally because we know 2 things. Geometry, meaning the flow configuration, and the scale analysis. It is shorthand for U infinity, L over nu, and the L in the subscript refers to the dimension that is swept by the flow. It's a very important word to keep in mind. Well, in convection, get to know the configuration. First, the solid shape, then the configuration of the fluid vicinity that matters. That's called boundary layer here. And then in that configuration, get a feel for the surface that suffers from the presence of the flow, and that is the swept surface. So L is not just any dimension, because the surface could be complicated, not a flat plate. It is the swept dimension. It is the surface from which the fluid scrapes heat, you see, like your blade on the windshield is actually scraping rainwater over and over again. That is a macroscopic, you can call it a metaphor for cooling, removing, in this case, heat from the wall. All right, so that is the answer to one of the conundrums. The second one was V infinity from the mass conservation equation. V infinity is, if you are interested, it's delta over L. And then times U infinity. And you can substitute this result here if you want. But it's better to, anyway, this delta, sorry, the V infinity is an exercise that you are free to contemplate on your own. More important, of course, is the money in the bank, which is predicting the friction force, namely tau. Tau is equal, as I wrote earlier, to mu, and then du dy at the wall. I have to be precise here. But in order of magnitude sense, it's mu, and then U infinity over delta. And we just figured out that delta is the length times the Reynolds to minus 1/2. So that means length and Reynolds to 1/2 upstairs. So that is the value of the skin friction. Yeah, friction force divided by the unit area of the skin of the airplane is called skin friction. It's kind of amazing that these airplane designers had to come up with the word skin, when in fact all friction is about, it's superficial. It's on the surface of my shoe, you see. Pretty cool, yeah. And I think that sole, the word in English, S-O-L-E, what's the origin of that? It sounds like maybe refers to the scale of the fish, you know, something that's superficial but solid. All right, let's see what we do with this tau, because a rule, incidentally, that's drilled into us by this exercise called scale analysis is the importance of expressing your conclusions in dimensionless form. If you converse in dimensionless form, you do not make the mistake of end up with a result that says, here is the weight of this bushel of apples, the weight of the bushel of apples, and on the right-hand side you have a number of kilograms. Kilograms means mass, not weight. Weight is a force, you see. In other words, you may be right in the farmer's market, but in a discussion in the university, it pays to be very careful about the meaning of the words that you exhale. All right, what is this tau in dimensionless form? First of all, I already wrote that tau has the dimensions of force per unit area. And to make it dimensionless, you divide tau by a quantity that has the same units. The elders, and this is from before Prandtl, already knew how to do that, and they knew a quantity that had the units of pressure, And that was the so-called dynamic pressure rise that's based on this U infinity. It is the kind of pressure rise that a wall feels if placed perpendicularly to the flow, not parallel to the flow. So the so-called pressure unit that's used as the denominator to down-dimensionalize tau is fictitious, it's arbitrary. It doesn't belong in this drawing, but it belongs in the treatment that's been inherited from these pioneers. And this dimensionless ratio is called skin friction coefficient, capital C. Let's see what we get. We get, in an order of magnitude sense, what I wrote here, mu infinity, mu u over L, times Reynolds to 1/2. And then this thing downstairs, rho, by the way, this is rho u infinity here for dynamic pressure rise. In other words, here's the free stream, U infinity, and here's the solid wall in front. The streamlines diverge upward and downward. And here, in this, I don't know what you call it, eye of the storm, the pressure value resembles this theoretical value. So that's the mental viewing that gave birth to this expression. Okay, so I have here a 1/2 rho u infinity squared downstairs. You notice I don't write the 1/2 because half is of the same order of magnitude as 1. You can retell my bank joke by comparing 1/2 with 2. Hey, I deposited 1/2. You owe me 2. It's the same order of magnitude. Let's see what we get from this. What we get is, first of all, mu over rho is nu. And then this u cancels that. So we get nu. I don't want to make a mistake here. I better check my notes. Downstairs, yeah, so it's nu. Downstairs I get L and U. And then Reynolds to 1/2. That's what settles at the bottom. And this leading factor is in fact 1 over the Reynolds number. Meaning that the object of the game, called skin friction, expressed in dimensionless form, C sub f, the skin friction coefficient, is a predictable number of order Reynolds to minus 1/2. And it is this, when it comes to measurements, because people could measure drag where the theory can be tested and then validated. This has been done to the hilt in the history of aviation. Aviation today comes from this discovery and from the laboratory of Ludwig Prandtl and his disciples. Some of those names, you'll see them in the textbook, and they'll be appearing on the blackboard very soon. This little equation has important implications, which are available visually. If you're interested in the effect of dimensions on wall friction, the only dimension here is the length of the swept surface. To vary L at constant free stream velocity means to vary the Reynolds number. And this capital C, which is another name for tau, behaves like a non-equilateral hyperbola, this way. This is what 1 over square root of L looks like. And now we begin thinking, where is the so-called friction concentrated? You mentioned knife. It is in the vicinity or immediately downstream of the cutting edge. Clearly, that is why the knife becomes dull. See that? That is where the what's the word? The rubber hits the road. It's in the vicinity of the leading edge. So that's important to know. Another practical, practical, from the point of view of the teacher, practical conclusion is to question the slenderness ratio, this delta over L, which turned out to be Reynolds to the power minus 1/2. Well, the slenderness ratio was assumed much smaller than 1. That is what slenderness means. In other words, boundary layer theory is this assumption. But what does it mean with respect to the assumed shape of the boundary layer region? Thank you. It means that the theory is valid when this, you put it on the other side, the Reynolds number to 1/2 is much greater than 1. Am I right? Yeah. Which really means that the Reynolds number cannot be small. If the Reynolds number, okay, for the left-hand side to be greater than 1 in an order of magnitude sense, it must mean that the Reynolds number itself, meaning that this quantity must be greater than 3, more like 10, or even greater. But 1 is 1. When you talk about L, or Reynolds number, you have to raise this to power 2, and then you get into the realm of Reynolds numbers significantly greater than 1. So even though the whole story begins with a drawing, which I erased, that was very humbly claiming to be slender, because you see a cross-section through a bar of chocolate is really not that slender. Not slender like a sheet of paper. Well, the boundary layer has to be like a sheet of paper. or even more slender, like the crust of Earth. Yeah, there you go. I never knew that my story about the eggshell would have an impact on illustrating today's lecture. Okay, folks, I have to pack up.